Hello, welcome back to this course on structure, stereochemistry and reactivity of organic molecules and intermediates, a problem solving approach. In the last lecture session, we were discussing the enolization of a carbonyl system in a cyclohexanone, keeping as the model, and then followed by the addition of an electrophile. Okay. Now, if I again go back to the very basic, that first of all enolization, let me just I will show you the model later on. First show you the picture of enolization, that what we are saying here, that the enolization involves the axial hydrogen. Enolization involves the axial hydrogen simply because the axial hydrogen is having a bond, sigma bond, which can interact favorably with the pi cloud of the carbonyl, okay, which is not possible for the equatorial bond. So, it is the axial bond or axial hydrogen which is lost in this fashion, okay, and that forms what is called an enolate. Although the enolate is now written in chair form, but actually it is not a perfect chair. It is a kind of, it adopts what is called a half chair form, okay, like this. So, this is the this is because that this carbon, that carbon, and that means these double bond carbons as well as the adjacent carbons all lie in a plane, okay, that has to be planar. And so, this is the geometry of the cyclohexanone, and this is the O minus, and now you have the addition of the electrophile. Suppose the E plus is your electrophile. Now, the E plus can be captured, there are two possibilities, one from the top, that is this one, or the E plus can come can be captured from the bottom side, okay. And depending on the on these two approaches, we have given name to this, and the name is basically that the first find out the carbon where the electrophile is attached, and that is in this case that is this carbon, the electrophile is attached at this carbon. Then go to the next adjacent methylene where there is a pseudo axial bond and a pseudo equatorial bond. And so, now if the electrophile is captured from the side of the axial one, that means parallel, basically it is being captured parallel to the axial bond. So, that is called parallel attack, and this is what is called the anti-parallel attack, okay. And there are consequences of the geometry that is involved in parallel as well as anti-parallel attack. So, what happens in parallel attack, you have this carbon as it takes up the electrophile, this goes up. So, that means now you have a scenario where there is a carbon that will be here, there is a carbon already there, and there is a carbon at this position. These are prefixed, okay, only that will go up. If that goes up, so that takes up a geometry like this, and this is typical of, if you complete the cyclohexane product, then that will be looking like this. So, this is what is called a twist boat conformation, okay. So, the electrophile will be added at this position, and this is a twist boat conformation, okay. And then naturally, where is the carbonyl? The carbonyl is at this position, and naturally it will not stay in this conformation. So, it will go to the more stable chair form, okay. So, if it goes to the more stable chair form, then you have the carbonyl, the electrophile, okay. The carbonyl is here and the electrophile is here. So, the electrophile ultimately occupies an equatorial position. Okay. So, this is the equatorial product. On the other hand, if you have anti-parallel attack, then the situation is that anti-parallel attack, that means your carbon, this carbon is there, this is prefixed positions, and this carbon will go down and that will somehow come, say suppose go down. So, that means you have a situation where there is a there is this carbon already there, another carbon already there, and you have another carbon going down. So, that is typical of the representation of a chair form. Okay. So, this directly goes into a chair form, and where is your this is the carbonyl that has gone down. Okay. This is the carbonyl that has gone down. This is the back one. This is the back one. So, the you have an anti-parallel attack. So, that is the electrophile, and this is the carbonyl. So, it goes directly to the product. You do not need any interconversion of the conformer. So, that goes directly into the chair form, and it is the axial product. Okay. So, that is an interesting fact that the equatorial product is more stable, but to go to the equatorial product, you need to go to the twist boat form, and on the other hand, axial one is the less stable product, but you can directly go access that going through the chair form. Okay. So, this is the basic principle of parallel attack and anti-parallel attack. Just remember, parallel attack gives you the equatorial product, but it goes through a twist boat conformation, whereas the anti-parallel attack gives the axial product, which goes through a chair form, directly into the chair form. Okay. Now, let us so in absence of any overriding factors like steric factors, stereoelectronic factors, what happens that both the products are formed in appreciable amounts. And another case, another important point that one has to remember is that if the transition state is early transition state, then it does not matter whether it is going ultimately through a chair or a boat form. Then also the product, both the products will be formed in appreciable amount. But if the transition state is a late transition state, then obviously the twist boat have higher energy than the chair form. And then there will be differences in the ratio of the two products. So, there you do not expect any differences if there is an early transition state, that means it is not the geometry is not very important, and if there is no other overriding factors like steric factor or stereoelectronic factor, okay, then we can expect both the forms in appreciable amounts. However, in real scenario that does not happen, as you know, that there are other factors that come into play, and that makes the products deviate from 1:1 ratio. Okay. So, let us do some examples. Okay. Bromination of steroids, of steroidal ketones, bromination of steroidal ketones. Okay. So, let us take a steroid molecule. We are not drawing the C or the D rings. If the keto form, it is a steroidal ketone. So, let us take the 2-keto steroid. Okay. And there is a methyl here, there is a hydrogen. So, it is a transfused ring junction, and you are trying to do. So, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And you are trying to do the bromination. So, that is one scenario. The other molecule that we have is the 3-keto system. Okay. And it has been found that there is a perceptible difference in the bromination product. And what is the difference? That in case of the 2-keto steroid, the product that is formed is an axial bromine. The product that is formed is an axial bromine. Okay. On the other hand, from the 3 ketosteroid 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the 3 ketosteroid, the product that is formed is the 2 equatorial bromine. So, the bromine goes here, okay, in the equatorial position. Now, whether how to analyze this dynamic stereochemistry, that is the problem. Okay. So, let us try to draw the enolate. See, the way to solve it is basically you have to go back and just analyze the products. If the products are given, from the products you can make out that what type of attack is taking place on the enolate, whether it is parallel attack or anti-parallel attack. If it is giving the axial bromination, halogenation, then definitely axial product is obtained via anti-parallel attack, right. And the there is a ketone here. The equatorial product is obtained in case of a parallel attack, if parallel attack is more. Okay. So, actually this gives the answer, but you have to now provide a reason for this, that why there is anti-parallel attack here preferred and why there is a parallel attack that is preferred over here. Okay. So, let us draw the, let us first erase these two because I need space. So, the enolate that is formed is this is from the 2 keto system. Okay. This is the enolate. And if you draw the true picture of a cyclohexene, if you draw the true picture, means true conformation, then that will be is basically equivalent to okay. This is again, remember, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. So, now this will be your 2. So, that will be O minus, this is 1, that is 2, 3, 4, 5 and then this is your the other, the 10, 5 is connected to, remember, 10 in the same ring. Okay. 6 is the carbon belonging to the B ring. So, now you have to draw the other ring. The other ring is basically, that will look like something like this. So, this is the scenario. Where is your methyl? The methyl is at this position. Okay. So, if I can use another chalk, another color, then this is your the front side, this is the A ring and that is the B ring. Okay. This is your B ring and then the C ring comes from this side. Okay. So, this way it goes. Okay. Now, see parallel. So, you have to find out where the electrophile is approaching or attacking. Okay. The electrophile is attached either this position or from the bottom. Okay. Now, which one is parallel and which one is anti-parallel attack? Okay. That you have to go for the, where is the axial group at the 4 position? The 4 position has axial here, hydrogen, and that is your equatorial. Okay. So, equatorial and axial. So, that means this is parallel attack and this is anti-parallel attack. Okay. Now, there is basically usually what happens, that anti-parallel attack, when you have anti-parallel attack may have some interaction with the some 1,3, it can suffer from 1,3 dipolar 1,3 steric repulsion. Like again I draw the only the cyclohexene geometry. See, if you have these O minus and anti-parallel attack means it is approaching from this side. Okay. So, now if you have a group here, large group, so that can hinder the approach of the electrophile from that side. Okay. So, you have to try to find out whether there is a big axial group at this point. Okay. On the other hand, parallel attack, this is the parallel attack. Parallel attack does not encounter such type of 1,3 diaxial interaction, because the closest axial position will be here, but that is too far away, because that is this 1, 2, 3. So, 3 carbon, it is actually 3 carbon away, but this is the one, this is 2 carbon, okay, away. So, that is the perfect orientation of a 1,3 diaxial interaction. So, that is your that you have to look that whether there is any 1,3 diaxial interaction, severe 1,3 diaxial interaction or not. In this case, there is only a hydrogen here. Okay. So, basically if there is only hydrogen, so then there is this, because the anti-parallel attack goes via the directly to the chair. So, in this case what has been found, it must be a quite a late transition state. So, what has been found that majority attack takes place from the anti-parallel side. Anti-parallel side attack means what? Anti-parallel attack means your electrophile will assume an axial orientation, and that exactly what happens, that you get a product which looks like this. This is your bromine. Okay. So, that is the first molecule that anti-parallel attack takes place, because in absence of any other overriding interactions, no such strong diaxial interactions. So, anti-parallel attack is taking place. That means it is actually probably a kind of a late transition state. Okay. The second one means the 3 keto system. Okay. So, let us erase the 2 keto system and go to the 3 keto system. The 3 keto system, basically the enolate will look like this. This is your enolate. This is the methyl. Okay. Put the numbering, it is always worth keep the numbering, otherwise you may lose track while drawing the actual geometry. So, this is the scenario. Now, you draw that cyclohexene conformation. So, this is the scenario. Now, this is your 1, that is 2, that is 3. So, this is the O minus, okay, and that is 4, then 5 and 10. And like before, you can now draw the B ring. The B ring will go like this. This is the B ring, okay, and this is your A ring. Okay. If I put a different color, this is your A ring, this is the O minus, and this is the scenario. Okay. Now, this O minus will come back, and this will grab the electrophile either from this side or from this side. Okay. So, if you are adding the electrophile at the 2, that means now you have to look at the okay, there is a, remember there is a methyl here at the 10 position. Okay. Now, you have to look at the axial and the equatorial bonds at the adjacent carbon. In this case, the adjacent carbon is 1. So, this is the axial and this is the equatorial. So, this is the parallel attack and this is the anti-parallel attack. Okay. Anti-parallel because this is now opposite to the axial, this approach is opposite to the axial hydrogen, which is at the any substituent could be there at the adjacent carbon, and this is parallel to that axial hydrogen. Okay. So, this is the scenario. Now, which one will be preferred? In this case, you see the anti-parallel approach suffers from a severe 1,3 diaxial interaction from this methyl. So, there is 1,3 diaxial interaction between the methyl at 10 and the approaching electrophile. And the approaching electrophile, and due to this factor you now don't get much of this anti-parallel attack. So, you will get more of the parallel attack. Remember, parallel attack will give you ultimately the this also tells you the alpha beta nature of the substituent. The substituent is coming from the alpha side of the ring. So, it is alpha and it will be alpha equatorial. Okay. And so, that is why the product what we drew here was a carbonyl here and an alpha equatorial bromine. Remember, that was the structure. Okay. And this is the methyl. So, that is a very good example of that in one case parallel attack is taking place, another case anti-parallel attack is taking place, simply because the carbonyl is at two different positions. One is located at C2 and in another time it is located at C3. So, that makes the difference. Okay. Now, let us take another example. This was halogenation. Now, let us take an example where alkylation takes place. Okay. Where alkylation takes place. So, the molecule is a decalone system. It is a decalone. It has got sorry, it is not a decalone system, it is a decalone, but the carbonyl is here, CHR, and there is yes, this is the starting material, okay, a decalone, but an alkylidene, a 2-alkylidene decalone. So, that will methyl lithium. Okay. So, what will happen? The sorry, a base, not methyl lithium, a base, and then suppose methyl iodide. Okay. So, the base will abstract this hydrogen, it forms the enolate, and then the enolate will be alkylated, methylated at this position. Okay. So, this is the C10 position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, the question is, what is the geometry of this product? Okay. So, let us try to draw the first the enolate. So, this is the enolate from this one decalone system, and if you try to draw it properly, then what will happen? You have now this actually this is the front ring from this side and this is the back ring. So, what you do in order to, now this is okay, I think. Let us see whether we can draw it properly. If we do this, so this is the double bond, this is your O minus, this is your double bond CHR, up to that point is okay, and your next ring. So, double bond carbons are basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, this is your 9 and this is your 10, and 10 is connected to 1. So, that is your 1. That means the next ring, that is basically you have to draw it in this fashion. I am sorry. This is your A ring. Okay. So, better not first draw the B ring in the cyclohexene, that conformation, and then complete the construction of the A ring. So, this is your A ring, okay, and this is the B ring. So, now you complete the numbering. This is 1, this is your 2, this is 3, this is 4, 5, and then 5, then you have to, 5 is connected to, there is some problem, just a second, 5 is connected to 6, oh sorry, I am really sorry, this is not 1, you have to do it in the opposite way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this way. Okay. So, 1 will start from here, okay. This 10 is connected to 1 as well as 5, but since 5 is connected to 6, so you have to do it in this opposite fashion. Okay. So, that is the molecule. Now, the question is, it comes back, and now there is again possibility of two approaches. One is the methyl plus can attack from here, or it can approach from the bottom. Okay. You have to find out which is parallel and which is anti-parallel. Okay. Which is parallel, which is anti-parallel. So, you see, you have to come to this, come to the next carbon. Okay. The next carbon is, you see, these are the axial hydrogens. Of course, it is, then that means this is the, just a second. So, this is the parallel attack, okay, because this is the axial hydrogen. This is the axial hydrogen. See, the carbon that is attacked, you go to the next adjacent carbon. In this case, there are 2 carbons which are attached at this carbon. Okay. So, there are 2 axial hydrogens. So, you can take any of these as reference. So, that is the electrophile approaching from this side is a parallel attack, okay, and electrophile coming from this side is anti-parallel. Okay. So, that part is clear. Now, the question is which one will be the favored one. Okay. So, this is basically you can see. So, this is your parallel attack. Why? Because I said that this is the axial hydrogens adjacent to the carbon which is being attacked by the electrophile, or where the electrophile is captured. So, this is the parallel attack. So, no doubt about that, and this is the anti-parallel attack. The question is which one will take place preferentially. Remember, what I told is that anti-parallel attack, you have to always keep in mind that the anti-parallel attack may be subjected to interactions, steric interactions, like 1,3 diaxial interactions. In this case, there are, I could see hydrogens at these positions, which are actually basically having 1,3 diaxial interaction. Earlier case, we saw only one hydrogen offering the diaxial type of interaction to a bromine. Okay. Now, this is a 1,3 diaxial interaction offered to a methyl. The methyl is obviously bigger than bromine, that is number 1, and number 2 is that there are 2 hydrogens now offering steric hindrance to the approach of this methyl plus. Okay. So, that says that the anti-parallel attack will not be favored. On the other hand, it is the parallel attack that will be favored. Okay. So, when you decide between anti-parallel and parallel, you just try to check whether the anti-parallel attack is suffering from any 1,3 diaxial interaction or not, severe 1,3 diaxial interaction or not. In this case, there is this 1,3 diaxial interaction. So, the bottom line is that your methyl is approaching from the alpha phase, number 1. Number 2, it will occupy an equatorial position. Okay. It will occupy an equatorial position. So, the 2-dimensional structure will be something like this. This is double bond CHR and this is the methyl, and this is the hydrogen. Now, you can draw the cis-decalin structure if you wish. Cis-decalin structure, not this structure, because in this structure you may be little confused that what is happening, because methyl is so this is the methyl and this is the hydrogen. This is the carbonyl, this is CHR. Okay. So, that is the one of the this is the preferred geometry, because methyl will try to adapt to the equatorial position. It is always flippable, this molecule can flip, the methyl can flip to the actual position, but that will be the less stable one. Okay. So, I think this summarizes this lecture session, where we have discussed the electrophilic bromination and alkylation of an enolate. We have discussed again what is parallel and what is antiparallel, and how judiciously you can distinguish between the preferential attack based on the parallel or antiparallel. Remember, parallel antiparallel is based on the axial nature of the substituent which is attached to the carbon next to the carbon where the electrophile or even it could be a nucleophile, we have not given any example, that is attacking at that position. Okay. Based on that, we decide parallel or antiparallel, and you have to remember that antiparallel attack may suffer from 1,3 diaxial interaction, and if that happens, then parallel attack will predominate. Okay. This also tells you that what will be the ultimate orientation, alpha or beta nature of the substituent that is entering into the system, either the electrophile, the bromine, or the methyl, or any other alkyl group. Okay. Thank you very much.